Hi everyone, welcome to the OpenCAPI Birds of a Feather panel session. Hopefully you've all seen a good few of the presentations, my keynote this morning and the OpenCAPI Track 2A thread. The panel session here is we're really just discussing OpenCAPI, its applicability to the high-performance computing world, a data-centric fabric for high-performance computing, alongside with the OMI, the OpenCAPI memory interface as well, that I was talking about in the keynote. Happy to take any questions on all subjects, contentious or positive or everything. So looking forward to a lively debate. So feel free to put questions in the Q&A. And you can start putting questions in right from now if you like. We're going to start with a couple more short lightning talks from Craig Petrie at BittWare and Oskar Mencer at Maxeler. But before we jump into that, I'd like to just give everybody a chance to introduce ourselves who are on the panel. So we have Oskar Mencer. Would you like to give us a brief introduction?
Sure. Oskar Mencer. I'm here, a new member at the OpenCAPI consortium. Very exciting to see all these new developments. I've been running Maxeler technologies for 17 years now, so it's been a long time. And before that was at Stanford and Bell Labs.
Thank you. Craig, introduction.
Hi everyone, my name is Craig Petrie. I'm VP of Marketing at BittWare, which is part of the Molex group of companies. I'm based in the UK. I've been with the organization 18 years now. Started as an FPGA programmer from university, and I've been programming FPGAs or involved in FPGA computing for 23 years now, and been involved in the OpenCAPI OpenPOWER initiative with Allan for the last 6 or 7 years.
Thank you, Craig. Marcy, your turn.
Sure. So as Allan said, I'm Marcy. I'm a senior engineer with IBM. I've been involved in both the Power 9 and Power 10 platforms from the perspective of a core designer. Most recently, I'm really focused on energy efficiency, so looking at ways that we're reducing that through design in the core in order to get that advantage that you've kind of heard about throughout the day on our energy reduction from the Power 10, from the Power 9 processor into the Power 10 processor. But in terms of this panel, I'm really going to be covering things on Mises flow as well as memory inception in the Power 10.
Thank you, Marcy. Alexandre?
Hi, everybody. Thank you very much for your attendance. My name is Alexandre Castellane. I'm working with IBM for a few years on supporting and helping people to develop CAPI and OpenCAPI situations. I used to be a radio engineer, so I've been working for a long time in analog design, analog world, radio activity. And for a few years now, I'm working with IBM. Very happy to help you design your new OpenCAPI systems.
Thank you, Alexandre. Okay, so that's the panelists we have. I'll just state again, please feel free to enter questions in the Q&A. We'll try to get them answered, both written answered, and then I will bring them in for the panel discussion. See if we can get a nice debate going around the various areas. So, but firstly, I'll hand over to Craig, who will give a brief presentation on BittWare's accelerator cards.
Thanks, Allan. Okay, I'm sharing screen now. Hopefully everyone can see that okay. I think this presentation will be about 5 or just over 5 minutes in total. So I'll try and pack as much in as I can there. I'd like to start by thanking Allan and organizers for providing BittWare with the opportunity to present today. OpenPOWER and OpenCAPI are exciting initiatives that we're very pleased to be involved with, and like Allan, hope for lots of lively debate on the subject. So I'll be providing a quick overview of an OpenCAPI enabled FPGA accelerator product, which we developed in conjunction with IBM. For those of you who are unfamiliar with BittWare, we're actually an amalgamation of legacy Nallatech and legacy BittWare. two of the leading suppliers of FPGA accelerator products in the market. We were both acquired by Molex and rebranded BittWare, the Molex company, about 2 years ago, roughly. Nallatech being acquired Molex 5 years ago. BittWare has a rich FPGA heritage dating back 30 years to the very birth of FPGAs. We address 4 main application areas, but for today's presentation, I'll focus on how we're using OpenCAPI for computational storage use cases. As part of Molex, BittWare has tremendous reach in the marketplace, and we're happy to be helping to spread the word on the benefits and the potential of OpenPOWER and OpenCAPI. BittWare, as part of Legacy Nallatech, we were involved in the very first incarnation of CAPI way back in 2014. The card you see here is a 250 SoC card, which is very new. This is a versatile product which allows customers to experiment with solutions which address the accelerator and the coherent network controller use cases that we see with OpenCAPI. It uses Ocxl connectors to support up to 2 OpenCAPI links to the Power9 host processor. Focusing specifically on advanced memory and coherent storage controller use cases, there are some clear market trends that we should highlight, which play into the strength and potential of OpenCAPI. Storage class memory is clearly here to stay, with many applications taking advantage of persistent memory capability. This is fueling advanced research, and now what we're seeing is the deployment of production systems based on OpenCAPI 3.0. At BittWare, we successfully collaborated with IBM on a new class of FPGA accelerator which supports an OpenCAPI-enabled hybrid memory subsystem, or HMS. There are many PCIe cards on the market which feature acceleration technology with mixed memory support. However, building on OpenCAPI provides many clear advantages, specifically the low latency, high bandwidth connection to persistent memory for applications which benefit from large memory footprints. Example applications there include database acceleration, of which there are many kinds. OpenCAPI removes traditional storage software and hardware bottlenecks, along with faster restart times, often with no or minimal changes to the application code. And the fruits of our labor with IBM is shown in a picture here. This is a photograph of the product we developed, which is the 250 HMS, HMS being hybrid memory subsystem. The card specifications are fairly straightforward. It's a full height, half-length, single width PCIe card, which you can see here is passively cooled. Things get very interesting with the memory architecture. So in total, we've got 4 types of memory on board the card. The main kind of star of the show is the Samsung ZNAND memory. You can see that here along the top. We also have Samsung DDR4 SDRAM. We also have SRAM inside the Xilinx FPGA, which you can't see there, but is underneath the heatsink on the bottom. And finally, we have Everspin MRAM as well. Now, each card can support up to 3 terabytes of ZNAND memory, which can be virtualized. Importantly, we are able to hit the target price between traditional SSDs and DRAM, making this product a very compelling platform for sequential workloads. At the moment, we're doing testing and work with IBM, and we're on track to meet an average read latency of 1 microsecond at a bandwidth of 20 gigabytes per second. And this, of course, is possible because of the OpenCAPI 3.0 high-speed serial interface. The 250 HMS is mechanically quite sophisticated. It's a very complex card mechanically, and that's because it uses a very novel and modular M.2 approach to house the ZNAND memories. The ZNAND memories is where the large application datasets will be stored in these 4 banks you see here on the left-hand side. The DDR4 SDRAM is soldered onto the main PCB, acting as a local card DRAM cache for the applications. And the SRAM inside the FPGA also acts as another card level cache. Finally, the MRAM is there to guarantee persistence during unexpected power losses. And in the image you can see here, this shows a server, which I think is the S924 server, with 2 of the cards populated. I think the server can take up to 4 cards. And of course, there's an OpenCAPI enabled platform here. So we have up to 25 gigabytes per second with OpenCAPI 3.0, which you can clearly see here on the right-hand side of the card connecting into the motherboard. As you can see in this diagram, the hierarchy of the memory on the 250 HMS card works well for sequential workloads. That's what it's geared up for. This is where we're prefetching from the ZNAND memory to the DRAM cache, and we're quickly accessing that across the OpenCAPI link to the Power9 processor. Initial host access to the ZNAND is about 5 microseconds. However, this will then level out towards 1 microsecond once the data accesses are flowing. For more information on the 250 HMS product, then please get in touch with BittWare. IBM is very much a driver of this product and this development, and I'm expecting IBM to share more details on application benchmarks and solutions using this powerful platform later this year and early next year. So thank you for the kind of power presentation there, a kind of short form 5 to 7 minute presentation. Thank you for your attention. And as Allan said, very happy to try and answer any questions which you have. If I can't answer them live, then I'll be sure to get you an answer as a follow-up. Thank you.
Thanks, Craig. If you can release your presentation, and Oskar can jump in.
There you go.
Thank you.
All right, give me a second here. Sharing the screen. Now,
Yeah. You're up.
Okay. Does that work? All right. Well, thank you everybody for joining our panel here. This is a great opportunity to bridge across the different aspects of the OpenCAPI ecosystem. We clearly need cards, we need memory, we need processors, but we also need applications. And so this is where Maxeler comes in. Here at Maxeler, we've been developing applications for FPGAs for the last 17 years. It all started with a dream at Stanford, where I thought, well, it looks like the transistors are going to shrink, the wires are going to stay large, so maybe we should focus on moving data or data movement optimization as opposed to optimizing operations and optimizing arithmetic units inside of microprocessors. And so that kind of drove my whole development of a data-centric high-performance computing activity. Starting in 2006, we deployed our first high-performance computing application on FPGAs. This is now a very long time ago. Nobody could have imagined that one can run 3D seismic imaging on FPGAs to manage circuits of that size, to manage many different FPGA cards in one rack. We focused early on deployment across a rack, on deployment in production, on numerical stability, on convergence, and all the other little problems that would arise when we hit the FPGAs. One of the key problems that we had throughout all of this time is communication with memories and communication with the processor. That was always too slow. And so we've developed a latency and bandwidth, to some extent, tolerant architecture that would allow us to mitigate some of the log that we had, the backlog that we had compared to the competition. I don't know if it's allowed to mention the competition in this panel, but They make these cards with lots of little processors on them, and they have their own memory they developed, and their own connection to that memory, and that gave them a benefit over the last 10 to 15 years that was really very hard to compete with. And so we had to build systems on the rack level and the box level to have a chance against that. Today, with OpenCAPI, with faster memories, with faster connection to the processor, we have a much easier time. And all of these different activities, not just for 3D imaging, but also high performance computing in finance and in physics experiments, in many other domains, will be able to benefit from this. So it's really exciting to have an OpenCAPI cable and OpenCAPI memory. I wanted to put forward the most exciting application that we have. This is a quantum chromodynamics simulation, which we managed to put onto an FPGA in many years of effort and collaboration, of course, funded by the European Union, deployed in Germany, in Jülich. And putting the whole numerics and acceleration and system versus card versus box trade-offs all into one solution. The one thing that we're limited on here is problem size. So we can deal with a certain size of problem, but that is not exciting enough for the physicists. And that's where OpenCAPI comes in. This is what it really will enable us to do. Instead of doing quantum chromodynamics on a small system, on just a few particles, we'll be able to do much larger particle systems because we can connect the different cards with a cable that is as fast as we're connecting to memory, with a connection to the processor, as well as using power processors, which of course will boost our CPU side significantly. So we are expecting a very significant benefit for many applications. I wanted to show two particular ones. So one of them is the quantum chromodynamics that we've seen on the other slide. Here we are simulating particles, in particular quarks, and the particles that they create when they kind of go together. And that really drives our fundamental understanding of the universe. It's a very fundamental application. And also slightly on the complicated side, if you think about the data structures we have to deal with here, we're looking at 5-dimensional cubes. That is really nasty once you put that onto a DRAM and you want to rotate it and you want to move it and you want to slice it in different ways. You want to do various operators on these kind of data structures. And so it's all about the memory, it's about the size of the memory system and the flexibility to configure it in a way that is most suitable for the application. It's all nice and good to build large supercomputers with a hypercube, but if you look at the actual application and you look at what it needs to be able to structure the interconnect of your machine to what your application needs brings a huge amount of benefit. Being able to connect FPGAs across a rack brings tremendous benefit. We've tried many things in the past. We've built PCI Express networks. We've built our own proprietary cables and connectors to go from FPGA to FPGA. All of these attempts are ultimately limited by volume that HPC offers and by momentum that one can drive in one application. So having an open source and welcoming ecosystem that has many partners bringing their own expertise together. Of course, we can't compete with a Molex on connectors or cables, and we cannot compete on building microprocessors with, probably the world's best team to do that at IBM. So being able to put all of these things together into the same environment is really what I believe is going to give us a chance for the next 10x of performance. For any kind of really data-intensive application, 3D imaging, for example, is not just in oil and gas, but also in medicine, in manufacturing, in many other places where we need to look into three-dimensional structures, understand what's going on inside of it. And that's where we need this super high-end computing. So here is the baby that we are trying to talk about here. We're trying to pitch the idea of a super high-end FPGA card connected via PCI Express, OpenCAPI, Ethernet, many different connectors, maxing out on DDIMMs, putting as much memory as possible onto the cards, building racks out of these with, of course, power processors on the other side. I believe soon we'll have Power 10 to use as an option here. And so with Power 10 on the one side, OpenCAPI, and a really powerful ultra high-end FPGA solution, many of these applications in high-performance computing that are really mission critical for keeping the world around and in a better shape would be really benefit from this. I didn't put it on the slide because this was kind of a last minute thing, but the latest discussions we've had in California are about predicting fires, predicting the spread of fires, predicting the risk of different areas of being hit by fires as they go around. So there's plenty of applications for ultra high-end computing that are really important. Looking forward to any questions at the panel. Back to you, Allan.
Okay, thank you very much, Oskar. That's great. All right, everybody. So that's the two presentations that we've had to add to the track that you've hopefully all seen, and my keynote at the beginning of the day. Please feel free to put all your questions into the Q&A panel, as I said earlier, and I'll go through the questions and read them out to the panel, and we can maybe get some discussion going on this. So the first question is from Bruno Mesnet. What's next on Power 10 for all FPGA accelerators? Question marks. Will OpenCAPI be supported on like on Power 9 or just for storage class memory? Well, actually, maybe Marcy or Alexandre. Marcy, would you like to give this one a go, since you're the Power 10 expert here?
Sure. I mean, I could start, and we can have others jump in.
Yeah.
You know, so OpenCAPI, right? It continues to evolve onto Power 10. There's, you know, OpenCAPI 4.0 and 5.0 features that have been added. Things like memory inception are also in play there. So we're definitely seeing that space continues to evolve. I think your question is probably a little bit more around, you know, system offerings, and that's kind of a little outside of my expertise. I would assume it would follow a similar structure to Power 9, though, where OpenCAPI is not going to be available in your first GA, and then would come on later in the IBM solutions. It's interesting to see what will evolve in the OpenPOWER space. Right.
At the system level, my understanding is that there will be OpenCAPI ports available, but in terms of full enablement. Alexandre, do you know any more details? Oh, you're on mute, Alexandre.
I was saying no, I couldn't comment on that. Maybe Brian could bring some.
Brian, would you like to jump in? You're a guest panelist.
Sure. Can you hear me okay?
Yeah.
Yes, we do.
Okay. Well, thank you for the question, Bruno. That's a good leader. So for Power 10, you know, from what I'm kind of seeing, SCM is an interesting segment to go after, just because from what I'm observing, that appears to be the one part of acceleration that multiple, let's call it consortiums, are gravitating to. Let's call it that. It's one of the lowest hanging fruits that are out there. You'll see CXL, for instance. I think their first adopters will be folks that are gravitating towards SCM. We've got that today, even on Power 9 with OpenCAPI M1 and some of the presentations that were done this morning, like what Christian was kind of showing with Thymesis and other folks, right? We've had some other engagements doing OpenCAPI M1. So in my mind, Power 10 is going to, STM will be definitely a bogey where people are going to want to keep on doing accelerated development on. We'll also have let's call it a forward migration path. So the accelerators that we're developing on Power 9 will forward migrate into Power 10, because that's basically an OpenCAPI 3.0, C1, and M1 type environment. We will also support the OpenCAPI 4.0 constructs as well, so ATC and EAC, which allows you to do DMA store ordering, as well as like an effective address cache will be supported. But we're not seeing a lot of people talking about. They really like the shared memory constructs, let's call it that. But the caching abilities, I have not seen a lot of folks gravitating to that in OpenCAPI nor anywhere else. So to me, those are nice features to have. I think you need to have those as you move forward out in time. But I think most of the folks are going to do kind of the strictly C1, M1 stuff like we're doing today. So I think that's going to continue on in the future. With Power 10, we're still going to go ahead.
Yeah, no, I was just going to say, so obviously the BittWare card's quite an interesting one. It's a hybrid memory one with the low latency NAND from Samsung, the ZNAND, and blending the DRAM. But that today, obviously, I presume that's still the C1 interface rather than M1, but potentially...
No, that's M1.
That is M1, okay.
Yeah, HMS is M1.
And potentially that, one thing I would like to add on the Power 10 is the Power 10 really introduces the OMI fully.
Correct.
Which is really, this is in my mind the big game changer. And OMI is effectively a subset of the OpenCAPI protocols, I guess. But 4.0 on Power 10 is bringing those two back under the one OpenCAPI roof, right? Correct, Brian?
Yeah. So if you look at from an architecture perspective, Power 10 supports 4.0, right? Which is inclusive of not only the 4.0 constructs, but like you said, 3.1, which is basically the OMI, and then you'll have microchips memory buffer implementation around Power 10, right? I mean, that's one fundamental shift going from Power 9 to Power 10 is doing memory buffer redrive chips, right, with 5 nanosecond type latency adders over just traditional direct connect DRAMs. But it'll also include the ability to continue to support the 3.0 accelerators that are being done today.
Right. So from my perspective, the excitement there, and it was in the Power 10 presentation at Hop Chips, which was also given today, I think, was obviously we're bringing the BittWare card, the storage class memory, and the 250 SoC is media devices. We're bringing that in through the OpenCAPI 3.0 interface today.
Yep.
Clearly, it could well be extremely applicable on the OMI channel. We can suddenly start to bring in this storage class memory type. So suddenly an OMI DDIMM based on the microchip in DDR4 can go up to about 128 gigabytes. But we already see that the BittWare card is 3 terabytes. So suddenly you can bring like 48 or 96 terabytes into one Power 10 with that approach. I guess we would need to upgrade the interface to be fully OMI or 4.0 compliant to bring that in. But the other significant thing today with the OMI DDIMMs is that we've already got the RTL. The OMI DDIMMs were actually brought up on Xilinx FPGA. So we've already got the host RTL. It's in GitHub. It's ready for anybody to use. And so you can actually, if on a large Xilinx FPGA with 128 transceivers, let's say you reserve 16 for your host connection or your OpenCAPI connection, PCI, or whichever you want to use, you can bring in 14 OMI DDIMMs, which gives you 800 gigabytes per second of peak bandwidth, which is twice the HBM bandwidth on a Xilinx FPGA. And it can go to 48 terabytes, not 16 or 8 gigabytes. So I think this combination of depth with the bandwidth of HBM is really what makes that piece of it compelling. And so we've been bringing it in through OpenCAPI. We're on a journey here, and that's the good thing. We're on a journey. We've established OpenCAPI. We've brought the OMI. It's all about latency, latency, latency. Number one is the latency, which has always been the focus of CAPI. And so I think that's the interesting dynamic. And I think Power 10 really does turn that on significantly as well. Marcy, you mentioned memory inception. So if you guys have only followed this track, you're probably wondering what Marcy's talking about. So you heard, hopefully you heard the phymesis flow, apart, disaggregating and borrowing memory. Maybe Marcy, maybe you can give a few more words on memory inception versus phymesis flow. What's going on there?
Sure, absolutely. So phymesis flow is really a prototype, right, on the Power 9 that Christian presented in the last session in this track. And at the same time, right, we've been developing Power 10 in-house. And there, what we're doing is we're really focused, kind of the same thought process you've got, low latency, high bandwidth. We're sucking a lot of the pieces into the processor on the die themselves, pulling a few tricks there, so that basically you're eliminating the two FPGAs and the Ethernet connection, and you're cabling a processor to a processor, where you're able to still steal that memory over from server B to over to server A, hop it into a window, so there's still no application or OS type requirements, and you're able to use load store semantics to access it. So that part stays the same, but you're really getting orders of magnitude less latency, higher bandwidth, and we're thinking you're in the range of 50 to 100 nanoseconds of latency hit on a short cable reach there, versus traditional RDMA type methods to kind of get across nodes.
So we've got it with phymesis flow. We've got it with memory inception, which also works, my understanding, is over OpenCAPI 4. So it's not just reserved for the SMP bus. We have, if you were building your own processor and you wanted to leverage OpenCAPI in OMI, you could potentially get this memory inception piece of it as well. That's all to do with OpenPOWER and licensing terms, and so I'm OpenCAPI. I don't know how much that will cost you for licensing, but on the basis Power is fully open, I'm hoping it is licensable. But we've got phymesis flow, which obviously works with the FPGAs doing roughly the same thing, and you can potentially add acceleration. So you can add either just a memory node or a compute node where the processor can still see and access and borrow the memory of the accelerator as well. So you begin to share memory much more effectively here, which is really quite exciting. So we really are looking at, the memory is the center of the universe here. This is a data-centric system. We've broken free of the CPU-centric hybrid approaches I was saying in my keynote. We're really focusing on that data-centric approach, which is, I think, is an exciting piece of it.
There's another question out there for you, Allan, that I think you should read from Paul.
Yeah, the second part. I understand that there will be no bare metal.
No, from Paul.
Oh, right. Okay, beg your pardon. Yeah.
Looking in the open.
Yeah.
This is an interesting panel one.
A lot of very interesting applications in research presented today. A common theme is that OpenCAPI and Power allowed them to solve problems they could not solve before, aka PSI and phymesis. How do your respective companies help OpenPOWER/OpenCAPI grow the ecosystem? So good question. Anybody like to take on that one?
Oh, I'm happy to start. That's all right, Allan?
Yeah, absolutely. Fire away.
Yeah, so since this is mentioning the research problems and applications that are hard to solve, I think OpenCAPI is a game changer in terms of what it allows people on the software side to do and the types of problems that we'll be able to solve with it. From a how do we deliver that, there are three components to this. One is, of course, software that could be available. We can make available software in the open source realm of high performance computing, or proprietary software that can be made available. At Maxeler, we've been porting high performance computing applications over to FPGAs as a service. And so we're offering that anybody who has a problem, some application that they cannot run a problem that they cannot solve, a problem that has no solution today. They're very happy to take on the challenge and move that over to FPGAs and show how to do that, as we've done for JP Morgan during the credit crisis, where with all of the computers they were buying from major vendors, they could not calculate their risk. And so we built a specialized FPGA machine for them to be doing that. That's then helped them through that credit crisis. We did a similar thing for quantum chromodynamics, where people are looking at larger and larger systems. So it's all about the transformation process. And on the one side, that can be a service. On the other side, there's an opportunity to build software libraries. And so we have a large stack of components. Once we get our hands onto an actual OpenCAPI system with an FPGA on it, we'll be able to create a layer of libraries that will allow anyone to take advantage of OpenCAPI power on the HPC level, on a floating point level, on a numerics level, on a multidimensional data set level. So there's a software layer needed, and that's where Maxeler is focusing. And of course, somebody would have to build the cards and the hardware, and that's where we're looking to companies like BittWare and Molex and IBM to provide their leadership on that front.
Yeah, and Oskar, that's a good segue for me. So I think that the BittWare and the Molex value proposition is fairly straightforward, but as Oskar says, in order to help people be very productive and successful at the application layer, the hardware and the firmware and all of that needs to be in place underneath to make that happen. And for many people, OpenCAPI and the other interconnects are all very new, so they've probably heard of them, read about them, but they may not have had a chance to actually experiment and benchmark with them. So for us, the way that I feel BittWare helps contribute to the growth of the ecosystem is we're all about enablement at the hardware level. So as Marcy said before, some of the functionality, which is temporary within the FPGA outside the CPU, is then sucked into the power processor. There needs to be peripherals, there needs to be acceleration cards, which attach into the system. And these cards are pretty advanced. We're really on the cutting edge of signal integrity and density, but we're also trying to make these hardware platforms available at an enterprise class quality level, where customers can confidently prototype and benchmark and then transition into deployment if they wish to deploy the combination of the processor and the card as a combination. So I think for us, we're very much on the leading edge of these exciting changes and helping to enable the market. And that's the way that we feel that we can contribute. We also, we spoke about, low-hanging fruits out there. One thing which is just a rule in the world is that, different customers want different things, right? Especially when it comes to FPGA and acceleration. Often the memory architecture, the type of FPGA, the interconnect, those can be customized at the hardware level. And so one of the things we also do is provide variants of our products, which allow the acceleration part of the platform to be optimized for the specific application. And that again enables new applications to be developed, which not many people may have thought of until the use case emerged. So that's how we feel we can contribute going forward, and we've been able to help some of that over the last 5 or 6 years.
Thanks, Rick. Alexandre, what's next for Ocxl? Are you going to bring OMI support and bring Phymesis directly into the likes of Ocxl, or are there other advances in Ocxl, like supporting Vitis, for instance?
Sorry, Allan, your English is too good. I missed some of your keywords.
Well, I guess what's next for Ocxl in terms of support on Power 10, bringing in maybe OMI into the FPGA, into the OCXL framework rather than just regular DDR4 DIMMs? Is there any, or support, you support HLS tool flows and obviously directly HDL today? I mean, for me personally, it'd be lovely to see the MaxJ compiler from Maxeler be compatible with your OCXL. But what about Vitis? You know, Xilinx have been doing a big push on Vitis. Will that simply drop in with OCXL? What can people expect from that?
Well, it really depends on the capacity we have to invest in developers, because this system is a living system. So everybody is welcome to contribute, of course, and it will really depend on the questions we will have, on the interest that we will have, and I'm pretty sure that a company will be willing to invest in any area where the maturity of the what do we call that, proof of concept will be great enough to justify that we invest in these developments. But it seems it's pretty open.
And your OCXL is all of it software, and RTL is open source on GitHub. Is that correct?
Again, your question is?
Is OCXL, the RTL and the software all open source? Yes. And on GitHub?
Yeah, the part of OCXL is completely open. It's basically architectured around the Xilinx Vivado tool. So it's pretty easy to go inside and adjust or modify. So
people could modify and contribute themselves as well as...
Sure, and they are more than welcome to do it. This is the goal of this framework, that people can go inside the scripts and they can propose any modification. We are used to work with branches. So for example, PSI has nicely offered the way to use UDP packets. We did not work tightly on that. And all the Ethernet UDP connection has been contributed by PSI in the GitHub. So this is an example, good example that shows that anybody can make this tool much better than it is today. And I think it's very nice to have a company that is hosting the responsibility of checking that everything is fair and it's under control. So there is a tracking of any branch. But it's very open and contribution are welcome for sure.
Okay, thanks. Oskar, I think you were going to jump in there.
Yeah, no, I was just curious more about the OCXL direction and maybe how it connects to OpenCAPI, OMI, and the HLS that we're driving, of course, on our side, how one could combine that. So maybe a few more words on that would be great. Allan, you kicked off something there, so it would be great
I think Alexandre
learn more about that.
Yeah, Alexandre gave quite a good answer there. But yeah, I certainly support the idea. It would be wonderful to bring OMI DIMMs into the OCXL framework. Mm-hmm. I think one of the points, in fact, there was a question that came up on the OMI DIMMs in terms of people that have already got applications on the FPGAs. It was asking, if they've already got an application with DDR4 DIMMs attached, and they could come across a card which has OMI DIMMs and more memory bandwidth, could they drop their application easily into the card and into the new card, and how much work would it be? So obviously, if OCXL have that, then that would be an interesting one. But one thing that I've been talking about with my responsibility as the OpenCAPI technical director is they already have Accxi interfaces on the OMI host for the FPGA, the RTL, but it's not directly compatible with DDR4. So it'd be nice to get a shim that somebody with an application could literally drop it in with the OMI shim to a DDR4 interface and then just recompile and away you go. I think that would be a good example.
That's certainly something that we could do here at Maxeler. Our interfaces are all Accxi compliant, as well as DDR. We have a DDR memory controller that could very easily be modified to provide that chain and that connection.
I think that's
that would be very little effort for us.
And that would make it easy for everybody that's already got working applications to play with a card with new OMI channels. I've got a few questions rolling in here, so let me just read them. Paula Coates asked, Oskar mentioned access to hardware as a potential roadblock, and Craig mentioned the complexity equals cost in brackets of the hardware. How do we solve both of these divergent problems? I guess that's Oskar and Craig.
Yeah.
Or everybody.
Well, on the access to hardware, what I meant is that we don't have a card with a large FPGA, OMI channels and 10 DDIMMs connected to it. We could have it. The technology would support an amazing solution here, but we don't have it right now. So I think it's a race against the clock to start entering the field and delivering systems with this technology to get the card like this up and running. And Allan and I, we've been back and forth on the design of such a card and how quickly we could make one. So I think this is well underway, but the sooner the better on getting an OMI memory card. I think that will be my answer to this.
I guess an easy way would be for the chip suppliers to lower their prices. That would be an easy way to create cheaper hardware. But in the absence of that, I think, to be honest, one of the things I'd like to see is a kind of tipping point in the market whereby as a hardware supplier, it's expensive for us to invest in new technologies if there's a possibility that they won't take off and there's going to remain a very small user base for that technology, because there's less customers that we can amortize the investment cost for that product across. So one of the things I think would be great is if OpenCAPI really hits its stride, solves a number of important use cases in the market, and the market and user base grows, then companies like BittWare, we can invest in new hardware capabilities more confidently, knowing that we're going to get more of a return across a larger customer base. And so that's a win-win for everybody. We can amortize our costs, we can get economies of scale as we build more hardware. Those savings can be passed on to customers as well to lower the unit price of the hardware they're buying. So I think success breeds success, and I think if OpenCAPI can continue to demonstrate the benefits, then the traction will happen and the cost reduction will take place as a natural function of the market economics. So that's how it should play out. But I think as people involved in OpenCAPI, we're all willing to invest to a degree just to overcome that initial inertia and help people see the benefits. So I think it'll take time, but I think that success is certainly one path to reducing costs for everybody.
Thanks, Craig. Brian, did you want to jump in? I see you give a live contribution on this one, or do you think it's covered?
No, I think that was okay. That was good. I mean, I think I answered a couple of them publicly already, but then Paul has another one.
Yeah.
Second one.
I'll jump. Oh.
The first one you just did the first one. But this is the next one.
Yeah. If you can click done on that first one. The next one is any option for partnerships between cloud providers and hardware providers to provide inexpensive cloud access to potential developers. This amortizes the cost across multiple users and multiple providers. I think Paul might have put that one straight in my lap, but I'll let others skip in here first.
I think that was targeted towards you, Allan.
No, but go on. Anyone else want to make a comment on that? So working with cloud providers and the likes, Craig, or anyone else?
Yeah, I think we're always open to that, and I think an on-demand type of model is what customers expect these days. They don't always expect to have to invest in on-premise hardware unless there's good reason to do so. So making the technology available like you have in cloud services, which are becoming more sophisticated, is definitely the way to go. So yeah, absolutely an advocate for that. And I think that goes back to what I said about trying to breed success here so that there's a larger ecosystem and more opportunities for all the players in the market. So we're certainly proponents of that. I
certainly agree with that. The big issue that, or one of the challenges we've seen is we've got all these different open bodies, and everybody's doing their own open thing, but open hardware is open hardware. Once it's open, do we need separate ones, is my opinion. And so one of the ones that has really got some traction is OCP, the Open Compute Project. And there's a lot of ODMs are involved, building real hardware, scaling up for the cloud providers and the hyperscalers. And they're donating, all of the hardware, from the BMC to accelerator modules to infrastructure chassis for these accelerators. All of these pieces are coming into play here. And but typically what's going on right now in the OCP world is everything's PCI connected, but we need to move towards these coherently connected buses, these more memory-centric buses that we're seeing. And so therefore they've got some idiosyncrasies. They can't work through a PCI switch. so effectively we could do with some optimization. So I think we could both leverage all the excellent work that's going on in OCP and not reinvent the wheel ourselves, and just do some incremental adders to that. Now, that is very likely very more tailored towards the cloud providers than some other pure aspects that you may want from a platform, like sheer performance per cubic inch. But that may actually get us nicely to, if we could get some hyperscaler adoption, that can give us some scale that can get the cost down, as you say there, Craig, and allow us to be successful. So I think I'm certainly trying to build more bridges between OpenCAPI and OCP and OpenPOWER and OCP, so that we can really get some more momentum in all the really truly open stuff. And I think that's a key way to go forward.
Maybe could I just ask a question as well?
Absolutely.
I was wondering how much support and interaction OpenCAPI has from IBM Cloud, the kind of primary driver of IBM in the future. Is there anything that can be said about OpenCAPI availability in the cloud, Power 10 availability in the cloud, and support for all of these standard and interconnections? Because if that was just available on there, that would clearly be a game changer for OpenCAPI.
Alexandre, I think you may be able to answer that with the Ocxl. You can dial into machines, and there's some. Are you familiar with what's available there, or?
I would suspect Brian would be more inclined to address this question. Would you, Brian?
Sure. So, and that's a good point, Oskar. And one of the things that like James and Mendy and Toshan are talking about, and I think they actually have a talk at 2:55 about Power Your Cloud. So I think Toshan might broach some of this stuff as well. But OpenPOWER definitely has a, let's call it a vested interest in making the accessibility of power machines, let's call it a lower barrier, right? And in my mind, that's inclusive of the AC 922s and the IC 922s, and having FPGA cards be part of hosting those platforms. The underpinning with that would be Ocxl, right, as the FPGA programming frameworks. And so I can't really, disclose anything publicly, but I know the overarching mission of OpenPOWER is to get a development cloud put in play. So, kind of stay tuned with respect to that, but we're kind of on the same page as you, Oskar, of where it needs to go, because the accessibility needs to be there. Does that make sense?
Yeah, yeah, that's great.
Okay.
Even now unmuted.
The one other thing just to mention just came to mind on the OMI and accessibility of hardware with FPGAs. So there is an FPGA platform internally codenamed Firing Ice that basically is a host platform with up to 4 OMI DDIMMs on it, and there's even a DDIMM with an FPGA on, so you could build your own memory buffers if you were interested in doing that. So it's both a testing platform, but it's a very useful bring up platform. So if anybody,
well, let me say it differently, Allan. So, okay. And you're right, partially. So there are open source contributions out there, right? Then you'll see it underneath github.com/OpenCAPI. There's a, let's call it a fire and a nice open source RTL implementations that were used for different purposes for testing the memory buffer. There are also FPGA platforms called Apollo and Gemini, right, that are related to Fire and Ice. So if you talk to, so if you attended, like, let's call it the memory work group within the OpenPOWER Foundation, right, and you talk to Kevin McIlvaine or, or Pierre-Luc, right, we do have FPGA platforms that we've used that they've also, I think, I don't know if they licensed them out or how they actually do that overall relationship called Apollo and Gemini for folks to take those Fire and Ice implementations on those two particular platforms.
Right. Yeah, no, well, he has, I understand Kevin's built a few more in terms of sharing.
And he has, right. He's building more to have on hand for relationships that kind of, let's call it, take that next step.
Right.
So that's all I wanted to correct you is, it's Apollo and Gemini, yeah.
Yeah, effectively what I wanted to say, if people were really interested in getting started with the DDIMMs on the FPGAs, then they're not ground zero of making their own board. They can start playing with IP and looking at the
exactly. Exactly.
Right.
Yeah.
Oh, we lost Craig.
He's back, I guess. Yep.
Okay, we're running close to the wire on time, I believe. I think we've got till 12:20. Annie, is that correct? I believe so. So I'm not sure if there's one more question in here. Oh, he sent me the schedule.
Yeah, I think the other thing I kind of want to mention too, Allan, is and it's been kind of reinforced, I guess, in multiple different talks about just the overall, spirit of what we're trying to do with OpenCAPI and working within the open source communities, right? We really recommend and encourage folks to download the implementations, take a look at them, provide feedback. I'm getting, more and more of that as we progress over time, but I encourage folks to take a look at them, invest some time understanding them. And if you find some things that don't work quite right, or if you have questions on them, or actually want to contribute back with, some simple modifications to make them better, I'm all for that. I mean, because that's primarily what we're trying to do with all these open source contributions is we don't want them to be necessarily IBM led the whole time. We did that initially, but we want the broader based community to be an active and vibrant community. And for all of us to be able to collaborate together. And so the more contributions that we can get, and I'll put and create the repositories out there for them, I think that only helps all of us.
Yeah. One other thing that's just come in here, thank you for the link, Paul. At 3:30, I'm not sure what track it's on, but Dan Jones from SkyTap will be talking about you can run Power on Microsoft Azure. So I'm not sure if that will include any OpenCAPI accelerators, but that's an interesting one I wasn't aware of. Apparently we do have till 12:25, so maybe I'll just throw one more question in there. Okay. Support open. I've got that one if I can buy it. There's one here. What is the power consumption comparison of 8 OMI channels compared to a single on-package HBM channel? Just on the HBM comparisons, obviously on chip with short channels is really pretty low power, obviously. So reaching out to 8 OMI channels would be a higher power requirement, I'm sure. But in terms of power density, you do have a power problem with all of these memories and very high power processors all on the one package. So actually being able to break out at the same or higher bandwidth in HBM, and being able to go to far greater depths than 16, 32 gigabytes or thereabouts really becomes very compelling. And the cost of the silicons, you know, the silicon substrates, these HBM enabled devices are not cheap in comparison. So I think I think there's a lot of opportunity there. In fact, my big vote needs a lot of money, but I really don't understand. You know, if you look at an HBM interface, it's actually got 8 ports on it, so it looks very much like 8 OMI channels. So you can have full compatibility from on-chip HBM all the way to storage class memory remotely connected through the memory fabric. So I would love to see the chiplet, the HBM logic layer interface, get rid of that very high pin count interface on the substrate, get 8 OMI channels on there instead, and then we can connect them with an organic substrate, so the cost of the packaged parts comes rapidly ramping down. So if there's a vote for me to go out there, is Samsung tear that logic layer out and put in an OMI logic layer, or IBM get it done, pay for it to be done, and then we could go OMI on package all the way to OMI remotely connected, and that, I think that would be the icing on the cake. If there any other comments on from a view of HBM from anyone else in the panels? I mean, it's great from its bandwidth perspective, but I think in the high performance computing world, maybe Oskar, maybe you can answer this, is how many problems, when you go memory bound, how many problems are okay with 16 gigabytes of memory, or how many problems really need to go much deeper, or what is the ratio? Would it be better to have a tiny processor with only a few flops but massive memory bandwidth? Or are we wasting flops in the devices? So what is that balance going on? Is there a need for this in the HPC world or not?
So that's a great question. I really like this question because we were at the core of that when we were working with the oil and gas industry, as well as now looking at climate and other simulations. The accuracy of any prediction depends on the discretization of space, time, and value. And I've been trying to drive that into physics as well, where originally physics, of course, only considers space and time, and they assume infinite precision. And then they hit the computer. And once they hit the computer, they say, well, wait a minute, there is no infinite precision. So what do we do with that? And then the initial answer, of course, for a few decades was, let's just use floating point IEEE standard and not worry about it. And we can see today that that is not possible anymore. So when you see Google making a TPU, some of my colleagues from Bell Labs actually over there driving that, you don't see floating point anymore. You see very customized number representations, which is discretization of value. And then you add to that discretization of space, where you have 3D, 4D, 5D spaces, depending on how crazy you go with the physics. You add time to all of this. Now suddenly there is more and more data to be considered, and you want to make predictions into the future. You want to say, is there global warming? Is it going up? Is it going down? The more memory you have on a node, the more bandwidth you have to that memory, the more accurate predictions you can make, the more accurate simulations you can run globally across the whole planet. And so it makes the difference from being able to simulate weather in California versus to simulate climate across the whole planet, including the oceans, including the air, including what goes around. So absolutely. But can it happen quickly? Well, that's the question, because scientists have to understand the capabilities of such new hardware. So they first have to build it, then they have to change the models, then they have to learn how to do business with these new models. And so the first step is on us to build these capabilities. Maxeler was first to be able to run 3,000 cubed seismic imaging on a whole rack of machines in production. The only way we were able to do that was through FPGAs and some crazy hardware that we were building at the time. That in turn enabled a whole other set of geophysics developments in terms of how they built their physics, their models, and how they do things in general. We then got overtaken by mainstream off-the-shelf hardware, which of course is always more attractive, especially if it comes at zero cost. But at the same time, the first step has to be showing that the capability is there, then people will find a use for it, absolutely.
Yeah, okay, thanks, Oskar. On that, we've overrun a little there, but thank you very much, all panelists. Much appreciated, in the audience for your participation. Much appreciated. Have a good rest of the conference. Bye.
Thanks, Allan. Thank you.